Chapter 8 of Advanced Algebra, where we have been looking at the exponential function. The exponential function having the form y equals a times b to the x. And in this lesson I want to look at two applications of the exponential problem or exponential function, and that is the half-life problem, which is a scientific application of the exponential decay, actually. And then we'll look at the second type of problem, which is what we call PERT, P-E to the R-T, which is a financial application of the exponential growth. So we'll look at the half-life problem. The half-life problem is a scientific application of the exponential decay. The half-life refers to the amount of time that it takes for a radioactive substance to decay to a point where only half of the original amount is left. And sometimes that half-life period can be very long, like thousands of years, and sometimes the half-life of substances can be rather short, a matter of hours. And so we're going to look at the application of that. Now, it is an exponential function, so you remember from our discussions earlier that a is the initial amount, b is the growth or decay factor, x is the time that has passed since the initial amount, and then y would be, what we have after that time has passed. Now, the half-life is simply an application of this, but with one little twist, and it's not really that big a deal. So, just to review, the y value is always going to be the amount of substance left after time has passed. So the amount left, okay, after time, which is the x that we put in, time has passed. So after x amount of time has passed, how much of the original substance will be left? A, as we talked about, is the initial amount, so this will be the initial amount of substance, alright? So the initial amount of the substance that we have. It might be, 20 grams of the substance, 150 grams, whatever. So the A will be how large of a sample are we beginning with. Now the B value is the growth factor, and because it's decaying at half or 50%, it'd be 1 minus 50 or half, so the B value for all half-life problems is going to be a half, so that value is already determined. Now the only kind of change here is that our exponent is x, but we're going to write the exponent as a fraction, so we're going to add a denominator to this. Alright, and the denominator is going to be the actual half-life of the substance. So this number will change for each problem. So this will be the half-life of the substance, because the time that we enter into for x, that's going to be a fraction of the half-life. So if the half-life is 1,000 years, how much is left after 300? Well, it's going to be 300 out of 1,000 years, so that would be 300 over 1,000. So x is still going to be the amount of time passed. Okay, so those will be the values that we put in for x, and the denominator of this exponent will always be the half-life of the substance. Now it's important that once we know what the half-life of the substance, we put the units or identify what the units are. So you'll need to write out what the units of the half-life of the substance is. In other words, if it's years, you need to identify that the half-life is in years. If the half-life is in minutes, it needs to be identified that the half-life is in minutes, because the x value that we substitute in, the time that's passed, has to be the same units as the half-life. So for instance, if the half-life of a substance is 4 hours, and we want to know how much is left after 10 minutes, well, I cannot put 10 into the expression for x if the half-life, the denominator, is in hours. So I need to change the minutes into hours so that this fraction has the same units. Without the same units, the calculation is going to be off. So you're going to need to indicate somewhere in the problem when you write the equation what the units of the half-life substance value is, so that the proper x value can be substituted into the equation. Okay, so again, nothing really different here as far as the application of the exponential. We still have the initial amount, we still have the growth or decay factor. The exponent is simply a fraction where we put in the half-life of the substance. So let me do one example for you. So for this example here, and this is an example that's in your book, we have 100 milligrams of a substance that we start with. The half-life of this substance is 6 hours. We want to know how much would be left after 75 hours. So the first thing we need to do is to write our exponential equation so that we can substitute in values. So y is going to be what's left. The initial amount is what we're beginning with. That's on a 100 milligram sample. So we have 100 milligrams to begin with. It's going to decay at a rate of half, and then my exponent is x over the half-life of the substance, which is 6. Now we need to write out here that this is 6 hours, so we need to identify that x is in hours, so that when we substitute values in for x, we make sure that we're only substituting in hours because we can't because the units of the half-life are in hours. So this would be the algebraic model that would represent this problem. Now I need to use this model to find out how much is left after 75 hours. So I simply substitute in 75 for x because this is in hours, the half-life is in hours, so I'm okay. So I'm going to have 100 times 1/2 to the 75 over 6 power. Okay, so we need to raise 1/2 to this power first and then multiply that by 100. When we do that, our calculation comes out to be about 0.017 milligrams is left. So there's going to be about 0.017 milligrams of this 100 milligram sample left after the 75-hour period. So that's how we do a half-life problem. Again, the exponential, the parts of the exponential expression are the same. We have our initial, we have our growth, decay factor, then we're simply substituting in values. Again, the only thing that changes really is this exponent, where we want to make this denominator the half-life of the substance. The second application of the exponential function is what we call PERT, and this is a financial problem. Now, there's only one scenario where we'll ever use PERT, and we'll talk about this more in pre-calculus perhaps, and that is if you're talking about interest that is compounded continually. So if we're talking about a bank account or a annuity or something like that, where the interest is compounded continuously. And this is the phrase that you must see in the problem, and if you see this phrase, then this is the equation that we want to use. A equals P times E to the RT. Okay, and again, this is an application of this exponential, so let me identify what the parts are. The y becomes the a, and again, the y in the exponential is how much is left after a certain amount of time. The a in here is the same thing. It's the amount of money that I have after time has passed. Okay, after time, which in this case is the variable t, has passed. Okay, so just like in the exponential, the y represents how much is left after time has passed. The a is simply taking the place of the y. The p in PERT is taking the place of a, and so this is what we call, again, the initial amount. This is how much money are we starting with. Now, this is in financial terms called the principal. Okay, the amount of money that you invest, an initial starting amount, let's say I want to put $1,000 in the bank account and then see how much money is left after a certain amount of time. The amount of money that I put in is called the principal, but in relation to the exponential, it's simply the initial amount. It's what I'm starting with. The B is taking the place by the letter E. Now E here is not a variable. E is a number. It's actually a number like pi. It's an irrational number. That number is 2.728, I think, or something like that. It goes on forever and never repeats. So E is not a variable. E is a number, and E is my growth factor. So E is taking the place of the B. So we have those parts. Now the X is being replaced by RT. Okay, so the exponent is not a single X, it's R and T. Time we already know, or T, is the time that's passed. R is our interest rate. Written as percent, change it to a decimal. Okay, so now this is different than the growth factor. In the growth factor, you remember, we had to add 1 to the interest rate, and that became our B value. In this problem, there's no adding 1 to this. We simply put the interest rate, whatever it is, right into the problem for R. R is not a growth factor like the B is, it's the actual rate. So R and T multiplied together are the exponent of this base E. So again, you can see we have Y equals A times B to the X, so this is an application again of the exponential growth function. But again, just a reminder, it must be and can only be used when the interest is compounded continuously, and we'll talk more about that in another lesson. So as soon as you see the phrase compounded continuously, you want to think PERT. You need to know what each of these variables represent. Remember, E is not a variable, it's a number, and is being raised to this power. And the second thing is don't add 1 to the rate here. That's a different type of problem. Okay, and again, that's where everybody makes their mistake. So again, let me do one example for you and then we'll wrap this up. So let's take a look at this example in our book. We want to invest $1,050 and we're going to receive 5.5% interest rate compounded continuously. How much money will we have in 5 years? First, because we said compounded continuously, my mind goes to this equation PERT. So I'm going to simply substitute in the values in the place that they go. The question is, how much will I have? So A is the variable that we'll be solving for. The P, or the principal, is the initial amount that we're investing. That's $1,050. E is my base, and again, that's a number. There's an E button on your calculator. It's right above the natural log key, or the LN key. The interest rate is 5.5%, so I need to change that to a decimal, so moving that over 2 places, that's 0.055, that's my interest rate, times T, which is the time passed, and in this case, it's 5. So this is my exponent, and so this is my equation. So now it's simply a matter of substituting this into my equation, making sure you put parentheses around that exponent so that it multiplies these together before it raises it to that power. So calculating that in my calculator, I have 1382.86, meaning I'll have $1,382.86 in 5 years. So I gain about $332 given this interest rate. So those are 2 applications of the exponential growth function, and we'll look at how to solve these exponential equations using logarithms in the next lesson.